Welcome, curious minds, to another deep dive. Today, we're plunging into the fascinating world of large language models, specifically focusing on, well, a really crucial area that's rapidly defining their capabilities: context engineering. It all started so innocently, didn't it? Feels like ages ago now we'd craft a prompt, just, a simple string of text, throw it in an LLM and kind of think, all right, job done.
Okay.
It was all funny in retrospect, like sending this super smart, but totally naive intern into, I don't know, the Library of Congress with just one key word and expecting to have a perfect PhD thesis back.
Yeah.
And then the realization hit. These LLMs need so much more. They need dynamic, structured, alive information to truly perform. That single string,
Yeah.
that was honestly just scratching the surface.
You've absolutely nailed the evolution there. What started as prompt engineering, which felt more like an art, finding the magic words,
Right.
has rapidly matured. It's become this formal, systematic discipline we now call context engineering. It's not just about the prompt anymore.
Not at all.
No. It's about the entire intelligent process, sourcing, shaping, managing the information we feed these powerful models, what we sometimes call their information payloads.
And when we say systematic, we really mean it. For this deep dive, we've gone through and distilled insights from over 1,400 research papers on this. It's a huge amount of work out there.
It really is.
And what we found was, frankly, a bit of a mess.
Sure.
Fragmented, brilliant ideas everywhere, but often siloed.
Right.
People working on one piece without seeing the whole picture.
Yeah, a lot of parallel work, not always connected.
Exactly. So our mission today is to build a map for you, a clear taxonomy, connect those dots. We're talking about how LLMs breathe, how they process, how they understand information. It's like designing a whole new brain for them, basically.
That's a great way to put it. We'll be breaking down context engineering into its foundational components. Think of them as the essential building blocks.
Okay.
And then we'll show you how these blocks are integrated into sophisticated intelligence systems, systems that are really pushing the boundaries of what LLMs can do.
And we'll also get into a really interesting challenge, right? Something you called a fundamental asymmetry.
Yes, exactly. A critical, almost poetic gap that all this innovation has revealed. It's becoming the next big frontier in AI research.
Okay, can't wait to get to that. But let's start at the beginning. Why? Why did we need to move beyond just prompting? What was the core limitation that really sparked this whole context engineering explosion?
The fundamental issue, really, is that an LLM's performance is just so deeply tied to the quality and relevance of the context it gets during operation, during inference.
Makes sense. Garbage in, garbage out, even for AI.
Pretty much, yeah. Simple, static prompt design. It was a crucial first step, don't get me wrong, but it's just not enough for complex real-world tasks.
Yeah.
It doesn't allow for dynamic, structured, and active information management.
Too rigid.
Exactly. And the field itself was fragmented. You had researchers looking at retrieval over here, long context over there, memory somewhere else, all in isolation. It obscured critical connections. Our sources, across the board, they highlight that a unified framework was urgently needed to systematize all these different techniques and really illuminate how they depend on each other. Without that framework, progress was getting, a bit haphazard.
So if I'm hearing you right, it's about making sure the LLM isn't just getting some information, but the ideal information for whatever it's trying to do.
Yeah.
Like a super efficient delivery system for knowledge.
You've absolutely got it. From an optimization standpoint, context engineering is basically about finding the best set of context-generating functions, the processes that gather and shape information to maximize the quality of the LLM's output.
Okay.
It's moving from that initial art of crafting a clever prompt to the real science of information logistics, giving the LLM exactly what it needs, when it needs it, in the best possible format.
So if we're designing this advanced info delivery system for an AI brain, what are the core parts, the absolute must-haves for it to make sense of the world?
The research really points to three foundational components. First up is context retrieval and generation.
Okay.
And this isn't just about writing the prompt. Crucially, it involves acquiring external knowledge, often dynamically.
So looking things up.
Yeah, think of it as how the LLM looks up information, or sometimes even creates it on the fly, pulling facts from a database, searching the web for breaking news, maybe summarizing a relevant document before it even hits the main model. It's that critical first step of assembling the facts.
Got it. And once it has that information, maybe even lots of information, what's the next challenge? Handling huge amounts of text must be tricky.
That brings us right to the second building block, context processing. This is all about how LLMs handle really long sequences of information, scaling up those context windows from maybe a few thousand tokens to potentially millions.
Brilliant. Wow.
Yeah, it's a huge leap. Historically, the transformer architectures that underpin most LLMs, they suffered from what's called quadratic computational complexity.
Sounds expensive.
It was. Basically, as the text got longer, the compute cost just exploded. It made processing truly long texts prohibitively expensive, as the papers say.
Like trying to cram War and Peace into a calculator.
Something like that. But here's where some key innovations really changed the game. Things like flash attention, and then flash attention 2.
Okay, what do they do?
They're clever. They exploit the way GPUs store and access the memory hierarchy to achieve something amazing. Linear memory scaling. Basically, making the cost grow linearly with text length, not quadratically.
Ah, much more manageable.
Much more. Without diving too deep into the technical weeds of non-matrix multiplication operations, the practical result is they effectively double processing speed in many cases. It makes feeding LLMs massive amounts of text actually feasible.
That's a huge unlock. But is it perfect?
Not quite. Even with these advances, we still run into this weird issue called the lost-in-the-middle phenomenon.
Lost in the middle. What's that? Sounds relatable.
It kind of is. It's this surprising quirk where LLMs really struggle to access or use information if it's buried deep in the middle of a very long context.
Ah.
They perform much better when key details are right at the beginning or right at the very end of the input text.
So they remember the first and last thing you told them, but forget the middle.
Basically, yes. And this isn't just a minor glitch. It can cause performance to drop by like up to 73% on tasks that really need that long-term recall or pulling specifics from big documents.
Wow, 73%. That's massive.
It is. So while we can feed them more information, the LLM isn't always reliably using all of it effectively. And context processing isn't just about length. It also involves things like self-refinement.
The model improving itself.
Yeah, where the model iteratively improves its own understanding or output, and also integrating structured information, like taking those knowledge graph triples, subject, predicate, object facts, like Paris is capital of France, and turning them into natural language the LLM can easily work with.
Fascinating. So it's way more than just stuffing text in. It's how you handle it, how you process it, overcoming these weird limitations. Okay, so once it's processed, how do you keep track of it all? How do you manage this potentially huge amount of context?
Yeah, that leads us to the third foundational component, context management. This covers strategies like memory hierarchies, sophisticated compression techniques, and various optimization methods.
Why compression?
To maximize the information density within the LLM's finite context window, you want the most useful information packed in there while still keeping it accessible. It directly tackles that fundamental constraint an LLM can only hold so much in its immediate working memory at once.
So it's about making the LLM's short-term memory super efficient and organized, not just a messy data dump. Are there any particularly cool approaches here?
Yeah, some really interesting ones. Many memory optimization techniques actually draw inspiration from biology, from how our brains work.
Like what?
Like implementing biologically inspired forgetting mechanisms. Think of the Ebbinghaus forgetting curve, the idea that memories fade over time unless reinforced.
Right, use it or lose it.
Exactly. These systems can selectively preserve or discard information based on how important it seems or how recently it was accessed. This helps the LLM prioritize what's truly vital for the current task, preventing it from getting overwhelmed by old or irrelevant details, especially in longer interactions.
Okay, that makes a lot of sense. So we have these building blocks: retrieval and generation, processing and management, getting info, handling it, keeping it organized. Now for the really fun part, how do researchers actually combine these to build truly intelligent systems?
Right, this is where it gets sophisticated. The research highlights 4 key system implementations where these components come together. The first one is probably familiar, but with a twist. Retrieval-augmented generation, or AGA, but it's ARGA smarter, much smarter.
Like, RAG got an upgrade. RAG 2.0.
You could definitely call it that. We're seeing things like modular edge architectures, think plug and play.
Okay.
They allow flexible composition of different retrieval components. You can swap modules in and out, different retrievers, different re-rankers to perfectly tailor the system for a specific task. Frameworks like FlashRag offer a toolkit for this. With core modules, you can adjust independently.
So much more adaptable.
Exactly. And ComposeRag even adds self-reflection, letting the system iteratively refine its retrieval strategy based on past performance.
Wow, so RAG isn't just fetching documents anymore, it's actively learning how to fetch better information. That's cool.
It really is. And building on that idea, we get agentic RAG systems. This is where you embed autonomous AI agents inside the RBAG pipeline.
Agents within RAG, how does that work?
Instead of just passive retrieval, these agents act like intelligent investigators. They can dynamically analyze the query, cross-reference information sources, even plan multiple steps, reflect on the results, and adapt their workflow. Think frameworks like React or Reflection. They interleave reasoning and action. The AI thinks about what it needs, then acts to get it.
That sounds like a huge step up. Like having a tiny research team inside the AI, actively figuring out the best way to answer your question, not just pulling the first thing it finds. What about this graph-enhanced AUG? You mentioned knowledge graphs earlier.
Right. This marks a significant shift. Instead of just relying on unstructured documents, it leverages structured knowledge bases, primarily knowledge graphs.
Remind me, what's the key advantage of knowledge graphs again?
They capture entity relationships and semantic connections explicitly. So instead of just text saying Einstein was born in Ulm, the graph knows Einstein is a person, Ulm is a city, and the relationship is borning. It's structured data. Systems like Caping or Carpa can retrieve specific, relevant facts, these triples from the graph, and just prepend them to the LLM prompt, often without needing any extra model training. And tools like ThinkOnGraph allow the LLM to perform sequential reasoning over the graph to find complex answers.
And the big win for the user here is more accuracy, fewer mistakes.
Definitely, that's a major payoff. Knowledge graphs can dramatically reduce hallucinations because the LLM's response is grounded in verifiable structured facts. That's not just making connections based on text patterns.
Right.
And they seriously boost reasoning capabilities, especially for those tricky multi-hop questions where you need to connect several pieces of information. The structured relationships provide something that raw text just can't.
This all sounds incredibly powerful, but it also sounds like these systems are juggling a lot of information. How do they actually remember things consistently, especially over longer periods or interactions? Are they building a persistent memory?
That's a critical question, and it leads us directly to the development of explicit memory systems for LLMs. Researchers are now designing systems that classify memory into categories, much like psychologists talk about human memory.
Like short-term and long-term?
Exactly. Sensory, short-term, and long-term. Short-term might be like a temporary cache for immediate context, maybe using a key value store. Long-term memory, though, involves external, persistent storage databases. Vector stores things the LLM can query to recall past information, much like we access our stored knowledge.
So they're really trying to mimic human cognitive architecture. That's ambitious.
It is, and interestingly, studies show LLMs with these memory systems exhibit primacy and recency effects, just like humans. They tend to recall information better from the beginning and the end of a stored sequence or conversation.
Huh. The similarities are fascinating, but how well does it actually work?
Well, that's the tricky part. Evaluating these memory systems is hard, partly because many LLM interactions are still fundamentally stateless. But benchmarks like Long-Meme-Evil are starting to give us insights, and frankly, they're a bit sobering.
Oh.
They show that even sophisticated commercial AI assistants can suffer a pretty shocking 30% drop in accuracy during prolonged interactions, especially when it comes to episodic memory, remembering specific past events in the conversation, contextualized with time and details.
Wait, a 30% drop. So even with these advanced memory systems, they can still significantly forget what you were talking about just minutes earlier. Well, it's relatable for coffee, but for an AI, that's a huge bottleneck for real-world use.
It absolutely is. It's a major ongoing challenge. Okay, moving on. The next big implementation is tool-integrated reasoning. This is genuinely a paradigm shift.
How so?
Instead of only relying on the knowledge baked into the model during training, LLMs can now dynamically interact with and use external resources. Think search engines, calculators, code interpreters, databases, specific APIs.
So the LLM isn't just a brain in a vat anymore. It can actually do things.
Exactly. Tools directly address fundamental LLM limitations, like their knowledge cutoff dates, a tool can get real-time information, or calculation errors, a tool can use a proper calculator, or needing to execute code.
Makes sense.
Frameworks like React, which we mentioned with agentic RAG, are key here too. They interleave the thinking steps with acting steps using a tool. And systems like Chameleon can even synthesize complex plans involving multiple tools, vision models, search, Python functions to solve really tricky problems.
That sounds incredibly powerful. Is it closing the gap with human abilities?
It's making progress, but there are still significant gaps. There's a benchmark called GAIA, designed to test these general assistant capabilities, tasks requiring common sense, tool use, multi-step reasoning.
And how do the AIs do?
Humans score around 92% accuracy on GAIA, the best tool using LLMs, even GPT-4. They're currently topping out around 15%.
15%. Wow. Okay. That puts it in perspective. There's still a long way to go for that kind of general capability.
A very long way. And it highlights the need for better ways to teach models how to use tools effectively. Approaches like reinforcement learning with systems like Retool are emerging to help models autonomously figure out the best strategies for tool usage.
So we need AIs that aren't just given tools, but learn how and when to use them optimally. Okay, what's the final piece of this puzzle when you bring multiple AIs together?
That brings us to the absolute cutting edge, multi-agent systems. This is really the pinnacle, aiming for collaborative intelligence. Multiple autonomous agents coordinating and communicating to solve problems far too complex for any single agent.
Like building an AI society almost, an AI project team.
That's a good analogy, and it requires incredibly sophisticated underpinning technologies. Communication protocols are vital things like MCP, which some have called the USB-C for AI because it aims to standardize how different agents talk to each other, and A2A for agent-to-agent comms.
Standardization makes sense for interoperability.
Absolutely. And then you need orchestration mechanisms, systems to manage which agent does what, when, and how they interact. Frameworks like OpenAI's swarm agent concept use real-time outputs from one agent to trigger actions or tool use by another. It's about managing the flow.
Sounds incredibly complex to manage. What are the big roadblocks here?
One huge challenge is maintaining what's called transactional integrity across these complex multi-step workflows involving multiple agents.
Transactional integrity. What does that mean in plain English?
Imagine that AI team working on a project. If one agent makes a decision based on information from another agent, but then that first agent forgets or misunderstands something crucial later on, the whole system state can become inconsistent.
So keeping everyone on the same page reliably throughout a long task.
Exactly. Preventing goal deviation because of miscommunication or forgotten context between agents. It's about ensuring the whole collaborative process is robust and reliable. Frameworks like SegLM are specifically trying to tackle this by providing better transaction support for these multi-agent systems. Stepping back and looking at all this intense research, handling massive context, integrating tools, coordinating multiple agents. It throws a critical research gap into really sharp relief. It reveals this fundamental, almost poetic asymmetry in LLM capabilities.
Okay, this is the puzzle you mentioned, the next big frontier.
Precisely. While today's models, especially when augmented with all these advanced context engineering techniques we've discussed, show truly remarkable skill in understanding complex context.
Yeah, they can follow incredibly complex instructions, connect distant ideas.
Exactly. They can parse nuance, track dependencies across vast amounts of text. But they exhibit really pronounced limitations when it comes to generating equally sophisticated outputs, especially long-form, coherently structured, novel creations that fully leverage that deep understanding.
So let me see if I get this. They can read and perfectly understand, say, a complex novel with intricate plot lines and themes. But if you ask them to write their own novel with similar depth and coherence, it falls short.
That's a perfect analogy. They can grasp the Mona Lisa, but painting their own masterpiece is still, well, not quite there. Bridging the gap between their profound understanding and their ability to generate equally profound, long-form, coherent output, that's arguably the defining challenge for the next wave of AI research.
That is fascinating. The input processing is way ahead of the output generation.
Okay, this obviously raises another huge question. With all these complex interconnected parts, retrieval, memory, agents, tools, how on earth do you even evaluate if it's working well? Surely old-school benchmarks don't cut it.
You're absolutely right, they don't. The sheer heterogeneity of context engineering components means static, simple metrics like BLEU or Rouge, which just compare generated text to a reference. They're fundamentally inadequate.
They don't capture the process. Exactly. They can't assess the quality of a reasoning chain or the effectiveness of tool use or emergent collaborative behaviors in multi-agent systems. And we already touched on the evaluation challenges for memory, that statelessness problem, the 30% accuracy drop in commercial assistance.
Right.
And for tool use, that GAIA benchmark showing the massive gap between human, 92%, and AI, 15%, performance starkly illustrates the limitations of current evaluation and capabilities.
So if the old ways don't work, what are the new approaches? How are researchers trying to get a clearer, more meaningful picture of performance?
The field is moving towards more dynamic and holistic evaluation paradigms. One important trend is self-refinement evaluation.
How does that work?
Instead of just testing a single output, you assess the system's ability to improve over multiple cycles.
Yeah.
Frameworks like self-refine and reflection literally have the model critique its own work, get feedback, and then iterate to produce a better result. You evaluate the improvement process.
Evaluating the learning, not just the final answer.
Precisely. There's also a push for multi-aspect feedback. And using specialized critic models, other AIs trained specifically to evaluate outputs based on detailed criteria like coherence, factuality, helpfulness, safety.
So AI evaluating AI.
In a structured way, yes. Ultimately, the goal is to move towards living benchmarks, evaluation suites that constantly evolve alongside AI capabilities, staying relevant as the technology advances, and tracking long-term autonomy, how well these systems perform reliably and safely over extended periods.
It's not just about being effective, but also safe, robust, aligned with our values, especially as they get integrated into more critical parts of society.
That's becoming paramount.
What really strikes me from everything we've discussed is that context engineering isn't just some clever technical fix or the latest buzzword.
Yeah.
It feels much more fundamental. It's like the emerging science of making LLMs truly aware of and responsive to their environment and history.
I think that's right.
It's about bridging that gap. We talked about bridging what these models know or can access with how they actually use that knowledge to reason, to act, and ultimately to create in the world.
Absolutely. This systematic approach to, well, information logistics and system optimization is truly foundational. It underpins pretty much every advanced AI system being built now, and I suspect all those yet to come. It's a field that's rapidly moving from focusing on isolated components to designing these complex integrated architectures.
And the challenges are growing just as fast.
Exponentially. It demands increasingly interdisciplinary thinking, combining insights from computer science, cognitive science, linguistics, systems engineering.
So for you, our listener, wrestling with how AI is changing things, as these models continue to evolve and weave themselves deeper into our work and lives, the core idea we unpacked today seems crucial. The idea that an AI's performance is just fundamentally determined by the context it receives and how it manages it, that's going to remain central.
It really is.
It provides a kind of roadmap, doesn't it, for understanding where intelligent systems are heading, from basic prompts all the way up to these complex multi-agent collaborations.
This deep dive, I hope, reveals not just the exciting technological leaps, but also the profound questions we're now grappling with. How do we truly enable AI to reason effectively, to remember reliably, to collaborate successfully, and maybe most importantly, to generate outputs that match their sophisticated understanding? It's about designing a much more intelligent conversation, both with the AI and within the AI itself.
And maybe to leave you with something to chew on. Here's a provocative thought for your own next step. As these AI agents become ever more interconnected, more autonomous, operating with these vast, dynamically managed contexts, what new forms of emergent intelligence or perhaps entirely new, unforeseen challenges might bubble up that we can't even predict right now? Something to mull over until our next deep dive.